Good morning. This is Mr. Potenski. We are going to be on page 68 of your Big Ideas Student Journal. Okay, so we're going to look at these problems. I accidentally made a mistake this morning. I thought I was recording and I streamed my explanations, and due to the fact that it's hard to erase in this book, we're just going to go with it. So here on these first two problems, we're determining whether the graph represents linear or nonlinear functions. So when we look at number one here, number one, uh, it's this graph. So in the graph, we want a straight line. That means we could put something up to it that we know is a straight edge and be able to see the line exactly run right along the edge. And here we can't see that. This is nonlinear, well, because the graph is not a line. All right. It actually is a square root function. If you're wondering what is that, I've never seen that before. It's what a square root looks like um, when it's graphed. For number two, so let's look at this again. If we can put this straight edge right up next to it, we see that, oh, this would go right along it. So we know that it's going to be a straight line. All right. So it is linear, and well, it's linear because the graph is a line. It is really that simple when we're looking at the graphs. All right. So another way a thing that we look at is tables. When we want to find out are tables, um, when we're looking at the tables, is a table linear or nonlinear? So the things that we want to determine to find out if something's linear or nonlinear is, does it have a constant rate of change or not? So if it has a constant rate of change in both the x and the y, then we know that it is linear. If it doesn't, well, then it's nonlinear. So looking at the first table, you'll notice I drew out the x is increasing by 1 every time, and then what is our y increasing by? So in number 3, we see that the x is increasing by 1, the y is increasing by 3, and if you're thinking about that in terms of rate of change for slope, that's going to be a rise of 3, a run of 1, so our slope would be 3. Um, so we see this constant rate of change, or the y is always changing the same for the same change in x. So we know this is linear, and we can say that as x increases by 1, y increases by 3, and that's every single time here in this table. So we can be like, yes, this is for sure. And it's important. I'm going to say this is important to have this always be 3 points that we want to look at this. Um, you need to, or um, three changes, because there is times sometimes where you can see that it increases by 3 and increases by 3 um, on other problems, uh, and it not be linear. All right. So here for number 4, we see that x is always increasing by 1. And then we have a y increase by -1, then it increases by 1, and then it increases by 3. Well, this should cue us in like immediately that, hey, this is nonlinear because our y is changing differently. It needs to be the same value each time. So as x goes up by 1, y varies, so therefore we do not have a constant rate of change, and that's why we're saying this is nonlinear for number 4. All right, for number 5 and number 6. So we're looking at equations. So how can we tell when an equation is linear or an equation is nonlinear? So if we can put it in to an equation of a line, then we are doing well. But if you can't, that means there's something wrong. All right. Um, so it needs to match up with the y equals mx plus b, or another form. So in number 5, we have y is equal to 3 minus 2x. So we rewrite that into our uh, y-intercept form. So y is equal to negative 2x plus b. We can write it like that. Our negative 2 is the slope. Okay, our 3 is our y-intercept. You may remember some of those things. But the key is our y is to the first power, our x is to the first power. Because when they're not, that means that it's not aligned. So let's look at number 6. So we're looking at that y is equal to negative 3/4 x to the third power. So what makes this, or breaks this, I should say, so that we know it's not a line, is that the 3, so the power of 3, any power that's not 1 on either our y or x immediately tells us this is not linear. So this is non-linear. And because we can't write it in the y equals mx plus b form, all right, and that into an equation for a line. Okay, so, and that's because the x here has no power, but our x up here has a power of 3. All right. Next up, we're looking at our graphs here. So we want to determine whether the function represents a domain that is discrete or continuous. So remember, domain is the possible x values of our graph. So here we have this line segment, right? And we can have any x that includes 1 all the way to 5, including 5. Okay, so to write that, we're going to write our domain as x values from 1, where x can be any value between 1 and 5, including those endpoints. So this is continuous. It's a continuous section because we can write it as that inequality, and it's continuous because it's a line segment is our reasoning there. Next, we look at number 8. We have individual points here where x values of 1, 2, and 3. So we can write that as x is the values 1, 2, and 3. This is discrete, and that's because the graph is individual points on that graph. When we have those individual points, it is very important to understand it's discrete. So whereas the other one is continuous, we have all the values in between those points versus just single points on specific values. Thanks. This is again the extra practice on page 68. If you have questions, please ask Ms. Kuhlman or Mr. Potenski, and have a great Monday or Tuesday.